So now we will discuss the last section of chapter 4, which is in fact something that I was proposed, or I was thinking to leave it till chapter 6, but then I think since we're going to explain an example, it's good to explain this chart. So this chart, or this method that we're going to discuss today, it's what we call the Makita-Wehe method, the Makita-Wehe chart. This is like an empirical correlation for a sweet gas that can be used to predict how much water you have in the gas stream. So imagine you have a gas stream, and you need to know how much is the water content, or how much is the fraction of the water in that gas stream. So based on the empirical formula, it's found that if you have a sweet natural gas first, and then this sweet natural gas has more than 70% of methane, and third, it has very little or very small amount of the heavy hydrocarbons, then if you plot the logarithmic of water content against 1 over absolute temperature for a specific pressure, you will get linear performance, or you will get linear line. So there's 3 requirements for this empirical correlation: that you must have a sweet gas, not sour gas, which means that you have very small quantity of H2S and CO2, and then you have more than 70% of methane, and the third one, you have very little quantity of the heavy hydrocarbon. Then if you plot the logarithm of water content against 1 over T, you will get, or 1 over the absolute temperature, you will get, for a specific pressure, you will get a linear line. And this is something that Makita and Wehe published it later on as a chart in order to estimate the water content for the sweet natural gas. But this chart will need some adjustment for the density and the salinity of water as well, and you have to keep in mind that when we adjust the density, or the adjusted density for the correction factor, or the adjustment for the density of the gas is not used actually to adjust for the CO2 and H2S content. No, we do not use the density adjustment for the H2S and CO2. We just adjust here 2 terms. We adjust for the salinity of water, and we adjust for the density of water, and we're going to see it later on once we apply this example, that we're going to summarize the whole use of these charts. Here's the Makita-Wehe chart that we already talked about to predict the water content based on the temperature, or absolute temperature, and based on the absolute pressure. For example, here you have the absolute pressure of 100 kilopascal, for example. This is here, for example, is how much? This is like 1000 kilopascal absolute pressure, and based on that data you can predict, or you can find how much milligram of water is available in the standard meter cube of the gas stream at the specific condition. And as we explained earlier, you need to do adjustment for 2 things. You need to adjust for the salinity of the water. For example, if you have a specific amount of water, let's say that you have 3% amount of salinity water, or for example you have 3% saline water, for example, or what we call like amount of solid in the liquid phase, or the solid salt in the liquid phase, then you can drag, or you can get one value of the first correction factor, which is going to be called as CS, which is the H2O from the brine over the H2O from the water, or the ratio between the H2O from the saline solution to the ratio of H2O from the water. And the second correction will be needed for the gas density based on this chart, and so you can, for example, know how much is the molecular weight or the molecular mass of the gas, and then you can, for example, if you know the temperature, how much the temperature in Celsius, for example, if you have 40, if you have 10, if you have 70, if you have 100, for example, here you have 160, for example, you can get how much is the correction factor for the density. We're going to see this, the details of how to use these charts later on in the example that I'm going to explain in this lecture. Now, how do you obtain the actual or the final water content of in the gas stream? You obtain WMW, which is the actual value, or the value of the water content that you obtain from the chart, and then you get 1 correction factor for the gravity and 1 correction factor for the salinity. Then you multiply all these factors with the values that you have read already from the chart. So the WMW, which is the value or the water content you read from the chart, then you multiply it by the correction factor to get the total water content in the gas stream that you have. And there are certain restrictions, such as, for example, when we talk about salinity correction, we are talking about approximately 4% brine solution maximum as the maximum. So we normally have to deal with a situation or the salinity of the water should be less than 4% in order to use the correction. And as a result, this correction will be around, this correction factor could be close to 1 or close to 0.91. And in terms of the density also, the correction factor for the molecular weight should be around 52 kilogram per kilomole, and the correction factor will be around 0.7. Now let's have a look at this example. You have a gas flow rate, or a gas or natural gas stream. You have natural gas stream that leaves an offshore platform. So imagine this scenario. You have here a platform or offshore platform, for example. Let me call it here offshore platform. Okay, and the gas leaving the offshore platform at conditions. So here the condition, you have 38 degrees Celsius. You have 300 kilopascal. Okay. Okay. And it goes to a specific location, or specific, for example, natural gas processing location. Okay, or what we call here in the question as the onshore. So here let's call it natural gas processing onshore. Okay, see the condition here at the onshore, let me just change the color. The condition here at the onshore, you have 4 degrees Celsius and you have the pressure of 6200 kilopascal. Okay, so the natural gas will leave the offshore location going to the onshore location, where the offshore location has a specific condition of 38 degrees Celsius, 8300 kilopascal, and the onshore one has 4 degrees Celsius and 6200 kilopascal. Okay, and you know that the gas stream is 2.8310 to the power 6 standard meter cube per day. Okay, and you know that the hydrate formation temperature, the hydrate formation temperature is around 18 degrees Celsius. The amount of the condensate produced, let me just change, the amount of condensate produced is around 56 meter cube per 10 to the power 6, or per 1 million of the standard meter cube of the gas. So for each 1 million of the standard meter cube of the gas, you produce 56 meter cube of the condensate. The condensate has a density. This is the density of the condensate. Molecular weight of the condensate is also given, and you need to calculate how much methanol do I need to inject to prevent the hydrate formation in the pipeline. So you have this scenario. You need to ship the gas, for example, from the offshore location to onshore location, where the gas has, for example, certain amount of the condensate, and the condensate will be produced in an amount of 56 meter cube per 1 million meter cube of the gas. You have 2.83 10 to the power 6 standard meter cube per day of the gas shipped from the offshore to the onshore. The offshore condition is 38 degrees Celsius and the pressure is 8300 kilopascal. The onshore condition is 4 degrees Celsius, 6200 kilopascal, and the hydrate formation temperature is around 18 degrees Celsius. So you need to calculate how much methanol do you need to inject in that case. So let's have a look at how can we solve this equation. So this is a good demonstration on how we're going to use all these charts that we were exposed to in chapter 4. So now let's start to solve this question. I'm going to solve it step by step. So the first step will be to understand how much water shall we remove, or how much water will be removed from this condition. As we explained earlier, that the gas will leave the offshore location at condition of 83, so 0.1, let me call it, which is the offshore location. You have the two conditions. You have the 38 degrees Celsius and you have the 83 kilopascal. And the onshore condition, which is point 2, you have the temperature is going to be 4 degrees Celsius, and you have 6200 kilopascal. So now I can simply, using the Makita chart, I can simply go and find how much water are available in this system. So the first thing I have 30, so at point 1, this is point 1. So point 1, the temperature is 38, so I'm going to go to the x-axis, the temperature. 38 degrees Celsius is approximately here, so I'm going to go vertically all the way. Okay, all the way. Then I'm going to look at how much is the pressure. It's 8300 kilopascal. So I have 8000 here, and I have the 10,000 here. So 83 will be somehow close, or up at a point close to the 8000, which is a little bit below the 8000 curve. So I'm gonna draw an estimation, or draw another line close to it, and I'm gonna predict that it's gonna be between 800 and 1000, 8000 and 10,000. So it's gonna be around this point, the intersection of the 2 points, the intersection of the pressure and the temperature. And this will be equivalent to approximately, so if I go horizontally, this will be equivalent to approximately 850 milligram of water in the standard meter cube of water. So you have at the inlet condition, at the first, at condition 1, which is the outlet of the offshore plant, you have the water content of the gas stream will be 850 milligram of water in each meter cube of the gas. Okay, now once it reached to point 2, which is, I'm gonna take another color. So point 2, which is the onshore, or what we called it as before as the natural gas processing plant on the onshore. So it has different condition where the temperature is 400 degrees Celsius and the pressure is 62 kilopascal. So let's start with the pressure. So the 62 will be less or little bit below the 6000. So here is the 6000 pressure. Okay, and the temperature for degrees Celsius will be approximately here, because this is the 5 here. You can see that this is 5. So this is the 4. I'm gonna go vertically this way, and where it hit exactly at this point. So I'm gonna read approximately a value of the water in the gas stream is equivalent to 150. This means that at initial condition, or I'm gonna call it water content at point 1, will be equal to 850, and the unit is milligram per meter cube. And it's important here to keep the unit. And W at point 2, which is the water content at point 2, will be equal to 150 milligram per meter cube, or standard meter cube. Therefore, the delta W, or the amount of water that will be removed, will be 850 minus 150, which is equal to 700 milligram of water per meter cube. So therefore now I can calculate how much water do I have to remove, or how much water did we remove from the the gas stream once it goes from the offshore plant to the onshore plant. So this means that how much water did I remove? So the total amount of water removed, total water removed will be equal to 700 milligram per meter cube of the gas, multiplied by how much is the total amount of the gas processed, is 2.83 10 to the power 6, which is gonna be, meter cube per day, which is equal to approximately 1.9 2.80 kilogram of water per day. So this means that once I process 2.83 10 to the power 6 standard meter cube of the gas per day, I remove from that 1980 kilogram of water is removed every day from this gas stream. So this is the first step. So this is the first step. And here, since we were given no details or no information about the salinity of the gas stream or the salinity of water, we tried our best to avoid how much is the, or to do the correction. We're gonna assume that there will be no need for a correction of the gas stream in terms of salinity or in terms of the density correction. So we're gonna assume that the correction factor, so this is gonna assume that the correction factor for the salinity of water and the correction factor for the density is equal to 1. So there is no correction at all. So now I'm going to go to step 2, or a second sub-step, or let me call it step 2. In step 2, if you still remember, we need to calculate how much we need now to do, or we need now to look at how much of the, because you remember that when we said that once I calculate the amount of methanol to be injected, I need to make sure that I have the two things. I have to keep in mind that some of the methanol will be lost in the evaporation, and some will be lost in the solubilization in the hydrocarbon. So I need now to know how much is the hydrocarbon, step 2. So step 2 will be to calculate how much liquid hydrocarbon. So for the liquid hydrocarbon, we know that we generate 56 of meter cube, I remember, is per 1 million standard meter cube of the gas. So I can simply calculate how much of the hydrocarbon will be reduced. Will be 56 multiplied by the 56, because you remember, let me just do it step by step, because this 56 will be, if you still remember the unit, 56, okay, it's 56, I remember, meter cube, our standard meter cube per 10 to the power 6 of the gas, multiplied by how much gas do we process per day? 2.83 10 to the power 6 of meter cube of the gas per day. So 10 to the power 6 will be cancelled with that 10 to the power 6, so you can get approximately of 158.5 meter cube per day. So this means that every day we produce 158.5 of the liquid hydrocarbon. And since you have the volume, if you multiply the volume by the density, which is already given in the question to be 778, or the density of the hydrocarbon or liquid hydrocarbon, this means that you can get the mass. And if you divide it by the molecular weight, which is 140, you can get the flow rate of the liquid hydrocarbon every day in a molar basis of how many mole you can get it per day. But here we calculate how much is the total volumetric flow rate of the liquid hydrocarbon that will be produced every day. Now we're gonna continue the question, and we're gonna go for step 3. Where in the step 3 we're gonna calculate how much is methanol in water you have. So now you have to keep in mind that it's given in the question that hydrate formation temperature will be around 18. But you are shipping the material or the gas to a location where the temperature is only 4 degrees Celsius, which is low below the 18 degrees Celsius. So delta T as a result will be equal to how much? 18 minus 4, which is equal to 14 degrees Celsius. So you have delta T, or the depression in the temperature, the depression of the temperature that's resulted from the addition of methanol should be around 14 degrees Celsius. So here it's very important to understand. Here we know that the hydrate will form at 18 degrees Celsius. But since we're gonna ship it to a location where the temperature is 4 degrees Celsius, so we have a depression in temperature. So we need to inject methanol in order to accommodate for this depression in temperature to prevent the formation of the hydrate due to the drop of this temperature. So the delta T, or the depression in temperature that we're gonna accommodate for or calculate the amount of methanol required to accommodate, is 14 degrees Celsius. So now how much methanol do I need, or how much will be the mole fraction of the inhibitor, which is Xi? So we're gonna do, which is the methanol, or the fraction of the methanol required. Okay, so now there are several methods that we can do it. We can do it graphically, straightforward, by saying simply on this chart, I have the temperature depression is 14 degrees Celsius, which is here. Okay, and I'm using methanol, which is this chart. This is the chart for methanol. I can simply go all the way down, and I found that my fraction, or the weight percent, or Xi from the graph, sorry, let me just write it down here. Okay. Therefore, from my graph, Xi will be approximately between 0.25 or 25% to 30%, so, and close to the 30%, so it's around 0.27 almost, or 275 almost, or you can even say it's 0.278 or 0.28 approximately. So this is how we calculate from the graph. But is there any other method that we can use to calculate? Yes, we can use the two methods, the Hammerschmidt, and we can use the Nielsen bucket. So we can use Hammerschmidt equation, which is again delta T equal to KH multiplied by Xi divided by 1 minus Xi multiplied by the molecular weight of methanol. Okay, so now how many pieces of information do we know? Do we know delta T? Delta T is given 18 minus 4. So this is delta T equal to KH. How much is the KH of methanol? It's around, if I want to go with the general one, it's 1297 multiplied by Xi, which is the information that I'm looking for, divided by 1 minus Xi multiplied by the molecular weight of methanol, sorry, which is 32. If you solve this equation, you will get Xi to be equal to 0.257, and this is, you have to remember that this is mass fraction. Mass fraction or mass percentage. So we solve this equation, or we solve Hammerschmidt equation, to find that the most massive fraction of methanol required to accommodate or to adjust or to reach this depression in temperature is equal to approximately 0.257, and if you do it from the chart, you get it approximately to 0.275. Now, can you use another method? Yes, we can use Nielsen-Bucklin equation, and you will get, and please try to do this at home, you need to do the calculation, and if you use Nielsen-Bucklin equation, you will get Xi, or X capital, but you have to keep in mind that in a Nielsen-Bucklin equation you will get X small, which is the mole fraction, and then you convert it to the mass fraction, will be approximately 0.277 fraction. So now we calculated how much is the fraction of methanol that will be in the liquid phase, that will be bonded with water. So once the methanol binds with water, the fraction of the methanol or the fraction of the methanol in the water, in that water methanol mixture, will be between around point, you can say 0.75, 0.275, 0.28 approximately. And from the chart here, as we here, it's like, I would say that it's not even 0.275 in the chart. It's around, you can say it's around 0.28 approximately from the graphical. This one should be, honestly, it's like, I can simply correlate it to 0.28 if I want to be in the safe side. Okay, as mass fraction. So now we have calculated how much is the mass fraction of methanol in the liquid methanol mixture that you have. Now the last step before we go to the calculation of the losses is to calculate how much exactly of methanol do I need to inject. Now I calculated from the previous slide, I calculated Xi, which is the mass fraction of the inhibitor, which is in this case methanol, to be equal to 0.277. So this is the amount, or the mass fraction of methanol in the methanol water mixture, which means that if I have the gas stream inside the pipeline and I inject methanol in it, so what will happen? The methanol will bind with water. So the Xi here is the mass fraction of the methanol in the methanol water mixture. So now I need to calculate how much is, in fact, this is as a flow rate, how much is the flow rate of the inhibitors, or how much of the flow rate of methanol that I need to inject on a daily basis. So I can calculate this simply by find the mass flow rate of water and multiply it by the Xi of the inhibitors divided by 1 minus Xi. And we know that the mass flow rate of the water on a daily basis is 1980 kilogram of water per day. So we calculated that this is the total amount of water that will be removed on a daily basis. Multiply it by Xi, which is 0.277 divided by 1 minus 0.277 in order to get an answer which is equal, where the mass flow rate of the inhibitors or methanol will be equal to 759 kilogram per day. Now we have calculated how much do I need methanol to inject into this gas stream to prevent the formation of the hydrate under the given condition that were given to us, if there is no losses. But we know the fact that there will be two mechanisms of losses. The first mechanism will be the evaporation. The second mechanism will be due to the combination or the solubility of the methanol in the hydrocarbon, or in the liquid hydrocarbon. So now we're going to calculate the first loss. So now we're going to go for the first loss, which is the losses due to the evaporation. And we know that we're going to use a chart for this, which is the chart that we discussed last time. We said that the use will be based on the final temperature or final hydrate temperature. So if you still remember this chart, we're gonna use this chart to calculate for the losses of methanol in the vapor phase. So we know that from this chart, we know that in the x-axis you have the pressure in kilopascal, and these small charts here represent the temperature. This is the temperature. Okay, so now I know how much is the pressure. We know that the pressure that we need to deliver the gas to has a pressure value of 6200 kilopascal. So let me just change. Oh, we can use the car. So we know that the pressure is equivalent to 6200 kilopascal. So as we mentioned earlier, this is the value of the pressure at the point where we are shipping the gas to, and the temperature at that location, at the onshore natural gas processing location, will be 4 degrees Celsius. So I'm gonna go and take this chart, the 4 degrees Celsius. Then I'm gonna go for the intersection and read how much is the x-axis value, which is 16.2, where the 16.2 is the kilogram of methanol per 10 to the power 6 meter cube of the gas per mass percentage of methanol in the water phase, which is the xi that we found. So now I found already that the x-axis value, let me call it here, x-axis value, which is the ratio, equal to 16.2 based on the condition that I have. And this 16.2 is in fact kilogram of methanol per 10 to the power 6 meter cube per percentage or mass percentage of methanol xi. So this is what this value mean. So this is kilogram of methanol divided by 1 million meter cube divided by the xi, or the mass fraction of the methanol. Therefore, if I find that this value is the ratio, then I can simply find how much is the mass or the total or the loss. Sorry, let me just. So I can simply now find how much is the loss of methanol through evaporation, or let me call it in the vapor phase, in the vapor phase. We have already know the pressure and the temperature, and we found how much is the ratio. Therefore, the loss of the methanol in the vapor phase will be equal to 16.2, okay, multiplied 10 to the power minus 6. And why is minus 6? Because it's per 1 million standard meter cube, multiplied by how much gas we process every day, 2.83 10 to the power 6 meter cube per day, our standard meter cube per day, multiplied by the percentage of the methanol, which is 0.277, which is in fact 27.7. So this will be cancelled with this, and as a result you will get the total losses of methanol in the vapor phase equal to 1,270 kilogram of methanol per day. So you can see that you need 759 kilogram per day of methanol just to bind with the water and reduce the hydrate formation temperature, and you will need 1270 kilogram per day of methanol through to the loss of methanol in the vapor phase or the evaporation. That's why it's so crucial for us to calculate how much is the methanol that's going to be lost due to the evaporation. So far we have calculated the amount of methanol needed to inject in the gas stream to prevent the hydrate formation. We have calculated the amount of methanol lost due to evaporation, and now we're going to calculate for the amount of methanol lost due to the second mechanism of loss, which is the mixing or the binding with the paraffinic hydrocarbon or the liquid hydrocarbon in general. And we're going to use this chart that we have seen before, where we're going to use the temperature and we're going to use the methanol percentage or the mass percentage of the methanol to get how much is the mole percentage of the methanol in the hydrocarbon phase. Okay. So the first step will be that we're going to use this chart. How do we going to use this chart? Now, first thing, now we need to estimate methanol loss due to hydrocarbons, solubility in hydrocarbons, solubility in hydrocarbons or liquid hydrocarbons. So now we're going to take the condition. How much is the temperature that we have? The temperature that we have is 4 degrees Celsius. So I'm going to go here. This is almost 2. This is 4. This is like 4 approximately. So I'm going to go vertically. Sorry. Okay. How much is the percentage of methanol, or the weight percent of the methanol? The weight percent of methanol is 27.7. Do we have 27.7? No, we have 20 and we have 35. So we have to imagine that we have a curve that's very close to the curve of that's between the 20% and the 35%. It's more close to the 35%. Now I'm going to draw this line using the purple color. So I'm going to assume that I have somehow a curve or a chart that's here, and that represent the 27%. So this is the chart that represent the 27.7% or mass percent of the methanol in the water methanol or in methanol water mixture. So now we get the intersection of the two charts, or the 2 points between the temperature 4 degrees Celsius and the 27.7, and I'm gonna assume that I'm gonna take this reading, and this reading will be approximately, I'm gonna assume that this reading will be approximately 0.15 almost, because this is 0.1 and this is 1. So you can see that if this is 1, this could be around 0.2, for example, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So this is like in between, or a little bit somehow the 0.1 and the 0.2, so it's around 0.15. So I assume that I found how much is the mole percentage. So the y-axis here, which is the mole percentage value that I found, is 0.15, which is the mole percent of methanol in hydrocarbons. Okay, so now we found that the fraction of methanol in the liquid phase, which is the hydrocarbon phase in this case, equal to 0.15. So now how do we calculate? How can we calculate how much is the amount of methanol? So we know that the molar percentage, or the molar flow rate of the hydrocarbons, we calculated, and we said that because we calculate it as a volumetric flow rate per day, and we said we can convert it to the molar percentage, and as a molar percentage, the molar flow rate for the heavy hydrocarbons or the liquid hydrocarbons is 881. So we can simply say that the flow rate, let me call it the molar flow rate of the methanol, equal to 0.15 divided by 100, which is 0.15%, multiplied by the 881, where the 881, sorry, just a second. Where this 881 unit is kilomole per day of heavy hydrocarbons. So the 881 kilomole per day is the molar flow rate of heavy or liquid hydrocarbon on a daily basis. How did we calculate it? We calculated from the first slide, or step 1, where we calculated how much is the liquid hydrocarbons that's flowing. We calculated in mass flow rate, and we said that this is the mass flow rate, or sorry, this is the volumetric flow rate, and you have the density and you have the molecular weight, and if you know these two pieces of information, you can calculate how much is the molar flow rate of the heavy hydrocarbons. So this 881 is the, let me just put it in green, this 881 kilomole per day is the molar flow rate of the liquid hydrocarbons. So how much will be the molar flow rate for methanol? As a result, it will be approximately 1.32 kilomole per day, which is equivalent, if you know the molecular weight of methanol, which is 32, which is, and you multiply this 1.32 multiplied by 32, which is the molecular weight of the methanol, you can get approximately 42.3 kilogram per day of methanol lost to the hydrocarbons. So now I can simply calculate how much is the total methanol needed. So total methanol needed, total methanol or inhibitors needed will be equal to how much lost in the hydrocarbons, which is 42.3, plus how much lost during to evaporation, which is 1270, plus how much do I need to add originally to bind with water, which is 759. And as a result, the total amount of methanol needed will be 2071 kilogram per day. And as you can see that out of the 2071 kilogram per day of methanol I need, I lose more than 50% of this amount will be lost due to the evaporation. So that's a good demonstration. That's a good example, hopefully, in order to know how to use all these charts and in order to know how to do all these calculations.